In October 2019, EPSILON published an updated orbit for the planet. They show that the orbit is slightly eccentric, with an eccentricity of about 0.26. The mass of the planet is 3.25 Jupiter masses, and it orbits at a distance of 11.60, with a period of 45 years. Epsilon Indi, Latinized from Epsilon Indi, is a star system located at a distance of approximately 12 light-years from Earth in the southern constellation of Indus. The star has an orange hue and is faintly visible to the naked eye with an apparent visual magnitude of 4.83.
It consists of a K-type main sequence star, India, and two brown dwarfs, Indi BA and Indi BB, in a wide orbit around it. The brown dwarfs were discovered in 2003. Indi BA is an early T-dwarf, T1, and Indi BB a late T-dwarf, T6, separated by 0.6 arcseconds, with a projected distance of 1460 AU from their primary star. In 1847, Heinrich Louis Dearest compared the position of this star in several catalogues dating back to 1750, and discovered that it possessed a measurable proper motion. That is, he found that the star had changed position across the celestial sphere over time. In 1882-3, the parallax of Epsilon Indi was measured by astronomers David Gill and William N. Elkin at the Cape of Good Hope. They derived a parallax estimate of 0.22 plus or minus 0.03 arcseconds. In 1923, Harlow Shapley of the Harvard Observatory derived a parallax of 0.45 arcseconds.
The star is among 5 nearby paradigms as K-type stars of a type and a sweet spot between Sun analog stars and M stars for the likelihood of evolved life, per analysis of Giada Arni from NASA's Goddard Space Flight Center.
Metallicity of a star is the proportion of elements with higher atomic numbers than helium, being typically represented by the ratio of iron to hydrogen compared to the same ratio for the Sun. Epsilon Indi A is found to have about 87% of the Sun's proportion of iron in its photosphere.
Epsilon Indi A has a space velocity relative to the Sun of 86 km/s, which is unusually high for what is considered a young star. It is thought to be a member of the Epsilon Indi moving group of at least 16 population I stars. This is an association of stars that have similar space velocity vectors, and therefore most likely formed at the same time and location. Epsilon Indi will make its closest approach to the Sun in about 17,500 years. When it makes perihelion passage at a distance of around 10.58 light-years, 3.245 pc.
Star has the third highest proper motion of any star visible to the unaided eye, after Groombridge 1830 and 61 Cygni, and the ninth highest overall. This motion will move the star into the constellation Tucana around 2640 AD.
Epsilon Indiae has one known planet, Epsilon Indi, with a mass of 3.3 Jupiter masses in a nearly circular orbit with a period of about 45 years. Epsilon Indi is the closest Jovian exoplanet. The Epsilon Indi system provides a benchmark case for the study of the formation of gas giants and brown dwarfs. During Project Ozma in 1960, this star was examined for artificial radio signals, but none were found. In 1972, the Copernicus satellite was used to examine the star for the emission of ultraviolet laser signals. Again, the result was negative. Epsilon Indi leads a list, compiled by Margaret Turnbull and Jill Tarter of the Carnegie Institution in Washington, of 17,129 nearby stars most likely to have planets that could support complex life.
In January 2003, astronomers announced the discovery of a brown dwarf with a mass of 40 to 60 Jupiter masses in orbit around Epsilon Indiae at a distance of at least 1,500 of. In August 2003, astronomers discovered that this brown dwarf was actually a binary brown dwarf, with an apparent separation of 2.10 and an orbital period of about 15 years. Both brown dwarfs are of spectral class T. The more massive component, Epsilon Indi b, is of spectral type T1, T1.5, and the less massive component, Epsilon Indi bb, of spectral type T6.
Evolutionary models have been used to estimate the physical properties of these brown dwarfs from spectroscopic and photometric measurements. These yield masses of 47 plus or minus 10 and 28 plus or minus 7 times the mass of Jupiter, and radii of 0.091 plus or minus 0.005 and 0.096 plus or minus 0.005 solar radii, for Epsilon Indi Ba and Epsilon Indi Bb, respectively. The effective temperatures are 1300 to 1340 K and 880 to 940 K, while the log G, CMS1, surface gravities are 5.50 and 5.25, and their luminosities are 1.9 times 10⁵ and 4.5 times 10⁶ the luminosity of the Sun. They have an estimated metallicity of m/h equals 0.2.
A visual search using the ESO's Very Large Telescope found one potential candidate. However, a subsequent examination by the Hubble Space Telescope NICMOS showed that this was a background object. As of 2009, a search for an unseen companion at 4 μm failed to detect an orbiting object. These observations further constrain the hypothetical object to be 5 to 20 times the mass of Jupiter, orbiting between 10 and 20 AU, and have an inclination of more than 20 degrees. Alternatively, it may be an exotic stellar remnant.
A longer study of radial, to or from Earth, velocity, using the Echelle spectrometer on the HARPS telescope, to follow up on END-L findings, was published in a paper by Kinemaster et al. In 2013. The findings confirm that, quoting the paper, Epsilon INDA has a steady long-term trend still explained by a planetary companion. This refined the radial velocity trend observed and indicates a planetary companion with an orbital period of 45 years. A gas giant with a minimum mass of 0.97 Jupiter masses and a minimal orbital separation of roughly 9.0 could explain the observed trend. 9.0 is about the same distance out as Saturn.
This does not quite qualify the planet as a true Jupiter analog, because it orbits considerably further out than 5.0 out. Not only does it orbit further out, but Epsilon Indi A is also dimmer than the Sun, so it would only receive about the same amount of energy per square meter as Uranus does from the Sun. The radial velocity trend was observed through all the observations so far taken using the HARPS telescope, but due to the long time period predicted for just one orbit of the object around Epsilon Indi A, more than 30 years, the astrometric phase coverage is not yet complete.